Okay, so we have another question from the second chapter of the Mechanics of Materials by Johnston, and we have aluminum shell that is fully bonded to the brass core, and the assembly is unstressed at the temperature of 15 degrees. Considering only axial deformations, we need to determine the stress in the aluminum when the temperature reaches 195 centigrade. So obviously, because of the temperature that is rising, we're going to have a deformation for the temperature change, which we know the formula is the delta T, which is the thermal expansion that we're going to experience. So it's going to be the length times the thermal coefficient of thermal expansion times the temperature difference that we see here. And this is going to happen for both brass and aluminum. But in the question, we have the coefficient for each of them. And if we have a look in these numbers, we see that the aluminum has a little bit larger value compared to brass, which means during this temperature increase, the aluminum tends to expand a little bit more than the brass, and that's going to create a force between these two since they are bonded to each other. So the aluminum, which I'm going to show it in this, is going to experience the compression force from the brass because aluminum wants to expand more, but the brass is restricting that, and also the brass is going to experience the same force in the opposite direction, which means the brass is actually in tension and aluminum in compression. So let's just do, I'm gonna do B in here just to differentiate these two. And what's gonna happen in here, we're gonna have a deformation because of this force P, as well as the deformation that we have from our thermal expansion. And the deformation for each of these two has to be obviously equal because they're bonded to each other. And it's going to be the elongation that is because of the force P. Let's go with aluminum first, and the deformation of the temperature for aluminum. And this has to be equal to same scenario for brass, and we're going to have delta T of brass. So these two, as I said, has to be in the equal value, and the difference between these two is that the aluminum is going to experience a negative elongation because it's in compression, and this value is going to be positive. So we just have to put these two equations equal to each other. So for aluminum, we're going to have negative PL over the area of aluminum, elastic modulus of aluminum, and this is going to be the alpha of aluminum times L delta T, and this will be equal to, I'm just going to write it in here, this is going to be equal to PL area of the brass, elastic modulus of brass, the thermal coefficient of the brass, L, and delta T. So as we can see, we can cancel out all the L's from the sides of this equation, and we're gonna bring this to the right side and this one to the left side. So from that one we can factor the delta T, so alpha A minus alpha B is equal to P over AB EB plus P times AA. Sorry, we have a plus sign in here. So on the right hand side we can factor P, so it's going to be P times 1 over AB EB plus 1 over AA EA. We're going to keep the left side as is, and we can just call this one simple ratio. Finding this is actually pretty easy because we have all the areas, we have all the elastic modulus in the question. You can see that we have all the E's, and this is going to be a simple value. And if we find that, we're going to get, I'm just going to show the values that we have for area. So the area of the aluminum, if we look at it, we have a hollow cylinder, so pi divided by 4 times the outer diameter, which is 60 millimeter, the inner is 25, so 60 squared minus 25 squared, and that's going to be millimeters squared, or we can multiply it by 10 to the minus 6 to get it in meter, and area of the brass. Same thing, this is a solid cylinder, there's no hole in the middle, and the diameter is 25, so 25 squared, again, times 10 to the minus 6. Can't find each of these areas, so pi divided by 4 minus 25 squared. So this is going to be 2.336 times 10 to the minus 3. So we have 2000. It will be cancelled out with this. And meter squared, and the other one is just 25, which is going to be 490.87 times 10 to the minus 6. Again, meter squared. So we have the area, we have the elastic modulus. If we just put that in there for that value that we have in here, we can call it actually maybe K, a constant. So our K is going to be 250.52 times 10 to the minus 9, and just have to figure out the unit. So area times elastic modulus is going to give us Newton, because we have Pascal, which is Newton per meter squared times meter squared. So this is going to be 1 over Newton. So just have to put the K in here. We have both of this, and the delta T is also 195 minus 50, which is 180 degrees C, and you just have to watch the unit of the alpha is 1 per degree C, which it is. So we just have to subtract those two, and if you do that, you're going to get our force P, which is 19.047 times 10 to the 3 newtons. And the question is asking for the stress in the aluminum, which is P over the area. But since, as we talked about, aluminum is in compression, so this is going to be a negative value. So 19.47 times 10 to the 3 over the area of the aluminum, which I believe we found it somewhere. So this value, 2.336 times 10 to the minus 3. So 19.047 divided by 2.336. And these are going to go on top. So 81153 times 10 to the 6 Pascal, again negative, so minus 8.15 megapascal as the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.